Good morning, everyone. So for the second day of our workshop, I'd like to take advantage to make a few remarks. If you have not submitted your poll for the breakout session, please do so. We have received many of them, but maybe not all. And Kurosh will send you anytime now by email the link for the survey that we need to ask you to fill. It's a request by NSF, but more importantly, it's an excellent feedback for us to help us to improve our workshop in the future. Especially this time, it's the first one that is online, so we would really appreciate your feedback. And I think now we will move to today's agenda. So the first topic today is to show you a short virtual walkthrough of the construction site of the LH Post 6. Since when we do the workshop in person, you know, we go there and people usually enjoy the tour to see the real thing. So we try to, with Kurosh, walk around the construction site and give you a feel for what is going on and what has already been built and what still needs to be done. So Kurosh, I think at this point you can start playing the video.
Absolutely.
Hello, I am Joel Conte, Professor of Structural Engineering at UC San Diego and in charge of the upgrade of our large outdoor shake table. So I would like to give you a tour of the upgrade, construction side of the upgrade, and focus on some important points. So let's go. So here we are at the Engelkirk Structural Engineering Center. We are arriving. We are pointing west. You can see here a large tent. We had to build these tents to store a lot of equipment, several hydraulic equipment mainly, since the upgrade is taking quite some time. It started, the project of the upgrade started on October 1st, 2018 and will end in late spring, summer 2021. Here you see the safety towers that we use when we are testing some specimen to prevent them from collapsing. All right, and here we are turning towards our staging slab. We had a second tent earlier here on that slab as well, but now you can see these two big packages that contains actually the two new horizontal actuators. Now we are walking back towards the shake table, and you start to see the platen of the shake table that is resting on four large reinforced concrete columns that were built just for the temporary storage of the platen. The platen weighs about 145 tons, and it will require some work, require some drilling of many holes to install the new wear plates underneath, and we have to do some machining on the underside of the platen to provide ideal surfaces to slide over the vertical actuators. And as we turn south, you can see the hydraulic power building. It's the same building that we had the last 15 years. It contains all the hydraulic power supply and the controller of the table. So we are going to have an overall look at the inside the reaction map. So you see a number of things here, a lot of piping, and the red pipes is the one that will have the pressure, the main pressure pipes. The red pipes, if you follow them, they follow a ring. We call this the main pressure ring. And the blue pipe are the return pipes. When the shake table will be working, the fluid inside the red pipe will be at 3000 psi. Inside the blue pipe, the return will be probably below 100 psi. You see, these are gigantic pipes. They have a 12-inch diameter, inside diameter. They are 1 1/4 inch thick. You also see a lot of smaller pipes. The smaller pipes you see red, blue, and yellow. So these are the pilot, the red and the blue are the pilot pressure red, pilot return blue, and the yellow one are the drain pipes. I'd like you to observe, these two walls that each of them support 3 vertical actuators. You see the steel base plate that will support the actuators. You notice that the plate that are at the end of each of the wall, so 4 of these plates, they had to be extended because in the 6 degree of freedom upgrade, the 4 corner vertical actuators have to be moved in by 10 inch to accommodate the new kinematic capabilities of the platen. So here you see the platen. You see these 2 large steel plates that will receive the head of the horizontal actuators. In the 1 degree of freedom configuration, they used to be fixed here. And now in the 6 degree of freedom configuration, there will be 1 horizontal actuators fixed here and the other one connected here. We are going to go under the platen to show you surfaces over which the vertical actuator will slide, the top of the vertical actuator. So you see these surfaces, they had rusted in the last 15 years. We just grit blasted these areas. And you see the one in the middle here. So there is 3 on each side. We are going to install some very large wear plates, 1/2 inch thick wear plates, highly polished, and we will have to maintain a planarity of plus or minus 24 thousandths of an inch of each of these 6 areas. Now under the platen here, you can see 2 very large, the 2 large saddle blocks that will allow to anchor the top of the hold down strut. Right? And we will have a new one in the middle. You can see that the one in the middle has never been used, in yellow here. And then at the other end of the platen, there is the existing one. So we will have 3 hold down strut to keep a very large overturning moment capacity. Here I would like to show you the northwest corner of the reaction mass of the shake table. You can see here that we are in the process of post-tensioning the large steel plate that serve as a base for the horizontal actuators that I'll show you in a second inside the reaction mass. But you can see here 6 post-tensioning rods with the nuts and the plates, washers. And you also see that we have grouted the volume behind the plates, between the plates and the reaction wall. And now we're going to go and look at these large steel plates that are inside the reaction mass. So you see one of them here that has been positioned. It has, now what needs to happen is we need to do some surveying work to have all the accuracy in the final positioning and then grout the spacing between these plates and the reaction mass. And we have 4 of those because now we're going to have 4 horizontal actuators. You can see the location of the other 2 that we will work on very soon. And now we are going to go inside the building, see a number of things. We are going to look at, we have 2 new pumps to supplement the existing 2-1. And we're going to look at the new accumulator bank that is completely installed and a lot of the new piping inside the building. So let's go. All right, so here we are turning around the west-south corner of the hydraulic power building. And you will see the 2 new pumps, brand new pumps that are being added to the existing two pumps. And you can see that we had to, of course, connect them to the cooling system. We have a new cooling tower. You see the brown pipes there for the cooling system and also bring the electrical power here. And now we are going to see next to this the brand new accumulator bank, very large accumulator bank, 75 bottles with a total volume of 10,000 gallons. So here you see they are in a group of 5 bottles. So we have 15 of these sub-modules. You can see that every bottle is monitored for the pressure with wireless pressure sensors. And this is basically these 2 pumps that you have seen. They are going to be used to mainly pressurize the accumulator bank, to push some oil at the base of each of the bottom below the piston until the nitrogen pressure, which is above the piston, reaches a pressure of 5,000 psi. In idle conditions, the pressure of the nitrogen in the bottle is 3,000 psi. So about 20-25% of the bottom of each bottle will be filled by oil. And that pressurized oil is the one that is used to control the horizontal and vertical actuators when we reproduce a multi-dimensional earthquake ground motion. And here below the catwalk, you can see clearly some red pipes. So the pressurized oil that is inside the accumulator bank is released through some blowdown valve, released into these red pipes, pressure pipes, that connect to the one that we have seen inside the reaction mass. And you also see here the blue pipes, and that's the return pipe, and you can see that they return the fluid at low pressure all the way to the surge tank. You see this large surge tank, we did not have to change it. We had sized it properly 15 years ago, thinking about the upgrade. All right, so now let's go and look at the cooling tower. We had to completely replace the old cooling tower that was close to the end of its life. Number one, and number two, didn't have the cooling power required for the upgraded shake table. So behind me, you see the cooling tower for the 4 powerful pumps that we have in the system. You see a lot of circuitry here, a lot of pipe for the water, and the electrical system support the cooling tower. Look at the size of the cooling tower compared to the building. It's pretty appreciable. We're going to go on the other side now. So here you see the 2 blue tanks here. It contains chemical that prevent calcification inside the heat exchangers of the pumps. This is a problem that we experienced in the past, and we don't want this to happen in the future again. So let's go inside the building. So here we have a very good view of, first, you see the 2 existing pumps. So one of them is going to continue to serve as the pump that is feeding all the pilot flows to control the spool of the servo valves. And the second pump will be also used to pressurize the accumulator bank. So we will have 3 pumps to pressurize the accumulator bank now. You see the top of the accumulator bank. Again, these modules of 5 bottles each. 15 modules, 75 bottles. You can see again the surge tank here. It's a 20,000 liter surge tank. So now we are going to go downstairs and go all the way to the bottom of the building to appreciate the size of the accumulator bank from their footing and the surge tank, and also follow the path of the oil from the accumulator bank all the way to the reaction mass. So now here you see the incredible height of this new accumulator bank. And again, the surge tank from below. And you see the 2 pressure pipes. Most of these pressure pipes were prefabricated by GS Hydro in Houston. One link that had to be welded in the site here is the one that I'm showing you here. So you see these 1, 2, 3, and 4 big weld, circular weld. The same thing for the second pipe in the back. These took a long time, and they had to be X-rayed as all the other weld. And these are, again, huge pipe, 12-inch diameter inside, 1 1/4 inch thickness. So you see, again, there they are coming out between the 2 accumulator banks here, which release the oil through some blowdown valve that we can see here in the view of the camera. With the 1 degree of freedom configuration, we used to have only one of these pressure pipes, and we had to double it. So now we are going to enter the tunnel, and you can see below these 2 red pipes, there are also 2 blue pipes that are the return pipes. You see that the tunnel is now occupied hugely by these large pipes. Now we are entering the reaction mass. You can see here the joint of the foundation of the building and the reaction mass. So we're on the south side of the reaction mass with a tunnel that brings the one pressure pipe and one return pipe towards the east, and then on the other side towards the west. And now we are inside the reaction mass. We have seen it a few minutes ago from above. So now you can see the big wall, the large wall here that is supporting 3 of the vertical actuators. You can also see the steel base plate that will support the vertical actuators. As I explained earlier, 4 of them had to be extended. You can see the extension here with rebars welded to the plate and anchored down to the concrete. We still need to grout this. We had to do this because the vertical actuator now in their new position will be 10-inch more on the inside than before to accommodate the kinematic capabilities of the platen with the new horizontal actuators. You can see here many of these large blocks called hydraulic manifolds. And at the bottom again, you can see now closer than before, again the red and the blue pipes, but you can see these large blocks with 3, 4, 5, 6, 8, 16. Each of them has 16 orifices, and these will allow flexible hose to bring the high pressure fluids to the servo valve of the horizontal actuators and get the return. And you can see here again from very close one of the gigantic steel plate to which the horizontal actuator will be anchored. So the swivel base of the new horizontal actuator will be bolted to these two plates protruding out that you can see here. This plate has not been grouted yet. Very shortly, in the next week or so, we will grout them against the reaction mass after a very accurate positioning. I'd like to bring to your attention, you see these opening into the reaction mass. First of all, the tunnel through which we came, and then you have the door on the west here, the door on the north, and the other door towards the east. This reaction mass has tunnel inside. It's not a solid block of concrete. Also, would like to show you this middle area between the 2 large walls supporting the vertical actuators. You can see these catwalks, and so we are going to replace the 2 hold-down strut that were here in the last 15 years. You can see here on the video the saddle, one of the 2 saddles that is anchoring the base of the hold-down strut to the bottom of the reaction mass. We will need to bring a 3rd hold-down strut that has already arrived. You can see it here. Under the blue tarps, we have the 2 existing hold-down strut, and under the brown tarp, we have the brand new one that has arrived on site a few months ago. And now that 3rd one will be anchored down in the same way as the other 2 in the middle to increase the overturning capacity of the shake table platen. So this concludes our virtual tour of the construction site of the upgrade of the LH post to 6 degrees of freedom. We will call the facility the LH post 6. We are right now on course to reopen the facility in July 2021. Very sorry that you could not be here in person. It would have been nicer. We hope that you will have a chance to come soon, before it reopens or soon after it reopens. Thank you very much for your attention.
All right, so hopefully this could give you a real feel of the construction site. So in the interest of time, maybe let's go now directly to the next item on the agenda, which is the 5th keynote presentation by Bill Holmes. Let me introduce him briefly when he gets set up. So Bill Holmes is very well known. He worked as a structural engineer for Rutherford and Check-in in San Francisco for 45 years before retiring in 2010. He's still very active as a senior technical advisor for the firm. He has been engaged on many projects with the Applied Technology Council over the last 20 years, most recently being the technical lead on ATC 78, seismic evaluation of older concrete buildings for collapse potential. He's also a member of the strategic committee of the NERI, National Coordinating Office at Purdue, serving as the chair of the Technology Transfer Committee. So he's a national authority on seismic code and design issues. He's a member of the National Academy of Engineering. Among many significant awards, he was awarded the Alfred Alquist Medal for Achievement in Earthquake Safety by the California Earthquake Safety Foundation, and the Brunier Award for Lifetime Achievement in Structural Engineering by the Structural Engineers Association of Northern California. So thank you very much, Bill, for participating to our workshop, and we look forward to your presentation. I don't know if you can hear us, Bill.
Okay, how about now?
Oh, great. Great.
Okay, sorry. Too many mute buttons here. Thank you for inviting me to your workshop, and I hope I can give particularly young researchers some ideas here. UC San Diego, it certainly does not need any lectures about technology transfer. They have that's been long a high priority, including having review boards and consultants, engineering consultants on your research. So the Technology Transfer Committee is really mainly directed at younger researchers that maybe don't understand the process and need some tips. If you're pre-planning a project, obviously research that has been already noted by the industry or standards as something that is needed, that kind of research is certainly going to be more easily implemented. So the question is, how do you find that? Well, I guess the science plan that NERI has produced was sent out to you. It is intended to be very comprehensive regarding a mitigation of risks or improving resilience related to all the natural hazards covered by NERI, and of course that includes high winds, tsunami, storm surge, and earthquake. I'm going to concentrate mainly on seismic because this site certainly has that focus. What are some other sources, perhaps, that you could get ideas? All the hazards have research plans of one sort or another. There's some links here that I think you're going to get the slides. So when you get the slides, you can use these links to get this various documentation that I'm going to show. But in the wind, there is a National Windstorm Impact Reduction Program that has a strategic plan. That program is run out of NIST, and so there is a similar thing to the science plan, only focused on wind. The tsunami also has a research plan produced by NSF and NOAA, and you got a link there. And then lastly, there is a Future Issues and Research Needs document that is now available on the Building Seismic Safety Council website, and there's a link there. I'll talk about this document a little bit more, and the NERP provisions that's produced by the Building Seismic Safety Council. So let's talk a little bit more about seismic. The NERP provisions is created every 5 years, and it's a feeder to the seismic provisions of ASCE 7, and the seismic provisions of ASCE 7, that's a loading document. That's pretty much required by the codes. So in a way, that when you produce the NERP provisions, it's directly related to going eventually into the IBC. Only it goes through ASCE 7 first. the NERP provisions is made up of 25 or 30 individuals, funded by FEMA. The travel is, of course, the work is all voluntary. So it's really the best place to get seismic research implemented, because it's supposed to be far future thinking, and so new ideas and concepts should go through the NERP provisions before it gets to ASCE 7. So at the end of every cycle, 5-year cycle, several documents are published as part of the NERP provisions. We just finished the cycle, so the latest version will be published actually probably within the next month or two. And the NERP provisions is made up of 3 parts. Part 1 is the actual changes that are proposed to be made in ASCE 7 that have been voted on over the 5-year cycle. And then with every change, of course, there's a commentary to that change. So part 2 of the NERP provisions is, in fact, the commentary that is related to those changes. And then part 3 is maybe not so familiar to people. It's called the resource papers, and it documents work that's been done by committee members that, for one reason or another, did not get into a proposal. So in order not to lose that work, this part 3 was created. And because it's, again, future thinking, those resource papers could contain, ideas for research that is needed. And then lastly, there's this future issues and research needs document, which I'll also talk about a little bit more, that is created by the members of the Provisions Update Committee at the end of every cycle, which documents issues that they've seen come up within the provisions over the last 5 years, and research that might be needed in order to solve some of those problems. So the resource paper document this particular cycle is quite long, and these are the subjects of the resource paper. You can see it's quite varied. There's concerns about the current mapping, the risk basis of the current mapping. There were several members that had sort of a minority opinion, so they have written about that. Of course, resilience-based design is a big concern, because it would seem to be obvious that eventually something like that is going to have to get in a code, and what is that going to look like? So there is a paper discussing that. It's a pretty comprehensive paper discussing what we know about shear walls and lateral earth pressure and so on. You can see these different subjects. A lot of concerns about diaphragms and lack of testing on certain kinds of diaphragms. So there's probably some good suggestions for research needs in those papers. Now that the other document, the future issues and research needs, is here is the website for that document, and some highlights. Certainly not all of the things that are discussed in there I'm not showing here, but some of the highlights is, again, the concern about functional recovery and parallel sort of design criteria for essential buildings to make sure those buildings will stay operational after an event. We really haven't had a lot of experience with such buildings other than the base isolated ones, so it's really not known whether our design simply with an importance factor of 1.5, or what that's going to do. There's a lot of concern about that. Another thing which is pertinent to UC San Diego is that there's a lot of interest in rocking structures, and there's really no design guidance of enough detail that would go into a code, so that is highlighted in this future issues and research needs. There are concerns about the vertical component of ground motion, and that yet is another subject that could take advantage of the new table in combination of the vertical component and the horizontal components. And Joel was talking about also there's a twisting motion that is of concern. That concern many years ago created the accidental torsion part of the code, and that's been controversial, whether it's big enough or whether it's needed at all. So that twisting capability of the table might be very useful for that issue. There's a lot of also concerns about duration of ground motion, and certainly in the Northwest, whether our provisions now, which are considering the large earthquakes, but California style, certainly not as long as we're expecting. And there's always problems with the design of non-structural components. This cycle, the forcing functions of the non-structural world were completely redone. A lot of work done by ATC to produce that change, but there's always a concern that is our implementation good enough? And it seems like most earthquakes show us that there's always a lot of damage to non-structural components, so that's always a concern. And interesting, the most common diaphragm that we have, a cast-in-place diaphragm, is actually not tested very much, mainly because I guess everyone thought that it is solid. But in order to put it on an equal basis with other diaphragms been tested, this Future Issues and Research Needs document is calling for some tests of cast-in-place concrete diaphragms. And finally, there's been some studies that show that the non-structural finishes of stud-framed buildings, steel and wood, that has a lot of sheetrock and plaster finishes that are quite strong and stiff, are interacting with the shear walls and might give us unexpected results. And this is both good and bad because the tests or computational tests show that it helps, and the buildings are much stronger than we expect, but on the other hand, it can create a weak story at the ground level because these walls were typically the same on every floor. So you finally get down to the first level, and it will become a weak story. There are many other ideas and needs. I just picked out some. The other assistance for implementation comes from our committee. Actually, that's why we were created. We have made one sweeping view of all research. NERI research, we're about ready to embark on another sweep of the research been done in the last couple of years. But we have other programs, so to speak. This is a little flyer here, which I know you can't read, but you can probably read it when you get the copy of the slides. But this basically is advertising the Technology Transfer Committee, and it's sort of aimed at young researchers. And this committee is about 20 volunteer people who are knowledgeable about technology transfer in all of the hazards: tsunami, wind, storm surge, and seismic. So we have sort of experts in all those areas on the committee that could help with the implementation. There's a lot of implementation ideas that are documented in another paper that we've written. And we're actually also offering brief conversations between young researcher or any researcher, as far as that goes, with the Technology Transfer Committee or a member of it to discuss, and I'm talking about maybe an hour or two, but to discuss implementation and how the research might be changed in some way or refined to make it more implementable. So that flyer is available. There's also one of the major efforts was a paper that we've written on the mechanisms for implementation of NERI research results. And this paper took a long time and is quite comprehensive. It goes over the common methods for implementing research results, specifically in the hazards area, and There's also, some of the members felt that researchers could frame their results in ways that make it more readily implementable, because sometimes you get the research results and there is some intermediate step that has to be taken by somebody or some group that translates the research results into more code type information. So those steps are sort of documented in there. There's an overview of how the existing codes and standards work. It's a mystery to students, I know. It's kind of a complicated world. And in the seismic world, as I mentioned, it goes from the NERP provisions to ASCE 7, finally to the IBC or the IRC. And we're also discussed, besides ASCE 7, we discuss ASCE SEI 41, which is the code, you might call it, the standard for existing buildings. We also give an overview of research implementation and technology transfer programs of major federal organizations that everyone's heard about, such as FEMA, NIST, and then private organizations such as ATC and Bssc. The NERP provisions is actually organized by Bssc with funding from FEMA. We also give some information on privately funded entities that have technology transfer activities. There's a number of these related to house construction. And there's also discussion about early adopters. An early adopter in this sense is most likely an engineering company that knows of some research results somewhere that is not in the code yet, but feels that this information could improve their designs, so they use it before it gets in the code. This particular method sometimes runs into trouble with local building departments, but engineers can often, through peer review or other methods, get their designs approved by early adopters. So if a research has engineers or a panel or a consultant from industry on their team, so to speak, or reviewing their research all the time, those engineers are the ones that are likely to be early adopters because they would be very familiar with the results. There's also some special issues when a research ends up developing proprietary materials, design methods, or construction methods, and we discussed that briefly as well as to how the differences of implementation when there's proprietary information developed. And lastly, we emphasize that presentations of all kinds are useful and necessary because nothing is ever going to get implemented unless somebody knows about it. So it's needed to give presentations on an ongoing basis about the research and the results so that the code or other people are going to implement it know about these results. The paper also stresses what I mentioned to start, that the industry involvement in research on an ongoing basis is very useful, and I know from personal experience that UC San Diego does this very successfully and has review boards and committees that are overviewing their research and making suggestions on how to make it more useful. So this particular paper is also available with this somewhat long, crazy link, but that was assigned by DesignSafe, so I have nothing I can do about that. But you can get that paper from that link, and I hope that the young researchers will avail themselves of that paper, because I think it has a lot of useful information for the young researchers. So thank you for inviting me, and I hope this was useful.
Yes, thank you very much, Bill, for a very informative presentation, very useful for young researchers in particular. So do we have any question from the audience for Bill Holmes? Okay, so there seems to be no question right now.
Okay, good.
So thank you very much, Bill, again, for your excellent presentation. So we will now proceed with the next item on the agenda, which is an introduction to the breakout session. So let me see if I can show my screen again.
Can I interject really quick while you're doing that? Sorry, this is Kurosh. If everyone can please send me a chat or a private chat so we don't fill up the entire chat with your top choice for the breakout sessions that we're going to be starting shortly. We're trying to pre-assign people to their correct rooms, and it would really help out. Thank you.
All right. So we are going to, let me see the time. So we are 9 o'clock. So we are right on time. So this is now the introduction to the breakout session. Then we will have the breakout session. There are 10 groups from 9:15 to 11, and then a break of 15 minutes, and then we come back to the general session. So here again, we mentioned that yesterday already, but we sharpened them a little bit yesterday afternoon. So the breakout session objective, you can see here 5 main objectives: identify high priority grand challenge research needs in earthquake engineering. So knowledge gaps that could be addressed with using the LH post with 6 degrees of freedom. Brainstorm on some example uses of the facility to tackle some of these grand challenges, and then help us, shape the future research programs and operations by utilizing the unique capabilities of the LH post 6, mainly to improve the seismic resilience of the built environment, and also identify possible mechanisms, to develop collaborations between industry professionals and academicians in structural and geotechnical earthquake engineering. Number 4 here, explore how the LH post 6 facility can support industry projects. And then 5, in which way the LH post 6 can fulfill the unique opportunity, I think, now to change, like we mentioned yesterday, the nature of seismic testing in the US and worldwide. So these are the 10 sessions that we have organized, and we had polled, the people who registered to the workshop early on to shape up these 10 sessions here. So those of you, like Kurosh mentioned, who have not responded to the poll yet, please do so. But right now, we have a pretty good distribution of people who chose this session as their first choice. We have 8 here, 7 on number 2, 4, number 3, 11, the largest one, seismic retrofitting of building structures, bridge structures, 5, earthquake protective system, 9, geostructures, 9, lifeline, 9 as well, non-structural component and system, 5, and seismic qualification of equipment, 4. So in each session, we have a moderator who has generously accepted to do the job, and a scribe. So
if I may ask,
yes.
Sorry to interrupt you, I'm sorry. Can we keep this slide up on the screen for maybe 1 more minute, just so
Sure.
everyone can see the list as well? Thank you.
Sure. So the scribe are all PhD students from our department. at various stages of their PhDs. You see here the name of the moderators. So the breakout session instructions that we send to the moderator and the scribes to develop a consensus on the 3 highest priority test program within your session area that can be addressed with the LH Post 6. And we have a number of suggested questions here, but you can of course add more. What type of specimen are ideal for accomplishing your research priorities? What resources are needed? How can the site help? Would hybrid testing help solve your problems? Would the reconfigurable test frame that we showed yesterday be useful in conducting your research program? And we have already in the last few months talked about a universal base frame that at some point will be needed. You have seen the new capabilities of the LH Post 6. We cannot, it's hard to resist comparing against the E-Defense. Some of you may already have done this. We have many parameters that exceed the E-Defense. We have maximum payload capacity of 2,000 tons. The E-Defense has 1,300 tons. They have a maximum displacement of 1 meter. We are now going to 89 centimeters. We exceed their peak velocity and so on, but they have a very large platen. Forgot the exact dimension, much larger than ours. But you have seen on some tests that Professor Restrepo, for example, showed yesterday, in the past we have used outriggers to extend, the size, the footprint of the specimen that we can test. So soon there will be we'll try to organize a workshop on and invite the community for whether there is really a need for, and if this is agreed on, how should we design, a universal base frame that extends the footprint of the platen. So if you could also discuss that, that would be great. And then identify any impediments for advancing your ideas. Of course, cost is always an obvious one, but imagine that the sky is the limit. And maybe some logistics that maybe I will refer to you, Kurosh. I think you want to give some information about the breakout.
Yes, please. Thank you. Thank you very, very much. This is Kurosh again, everyone. So we are currently in the process of assigning everyone to their appropriate breakout rooms according to our polling results. Once again, I'll reiterate, if you haven't already submitted the poll, if you submitted the poll, then you're fine. We'll take your information from the polls. But if you haven't, please send me a private chat through the Zoom chat feature, and we will assign you to your preferred breakout room. Once we start the breakout rooms after the break, you're going to get a little pop-up that's going to show up on your screen, and it's going to say, you've been assigned to this breakout room, and you can just click the join button and it'll put you inside that room. Once you're in there, you'll have the option to unmute yourself. If you want to turn on your webcam, if you want to, share some slides, you will have those options within your breakout rooms. Now, when the breakout room sessions are ending, you will get a notification on your screen. It'll give you 60 seconds, a heads up saying, we're closing out these rooms, so wrap up whatever discussions you're having and be prepared to leave. When you're done with the breakout rooms, it's going to bring you automatically right back to the main room. So you don't have to, click on any links or anything. If you choose to leave the breakout room at any time, you can go ahead and leave it and it'll bring you back to the main room, but you'll just be sitting there in the main room. There's nothing happening there. That's where, you'll just be. If you have any difficulties, if you get kicked off, or if you try to log back in and you won't get put in your correct room, please contact me either through the chat feature if you're already in the Zoom, through Zoom, or just shoot me an email. My email's on the screen right now, and you should all have it by now. I'm checking my emails regularly, so I'll be available to help out with any problems. And that's about it.
Thank you very much, Kurosh. And I forgot to mention, here on the first bullet, so one of the tasks of the moderator after the discussions and so on would be to meet with the scribe who will take notes all along and prepare 1 or 2 slide maximum PowerPoint with the summarizing the main key ideas that are in the second bullet here, and presenting it back to the main session. And I'd like to insist on this because there are 10 groups, so even 5 minutes each would be too much, because we would like to leave as much time for a good discussion after these these summaries come back. So if you could really try to stick to 3-minute presentation, so basically 1 or 2 slides, we would really appreciate, so that we have enough time for discussion. So I think based on that, we can go to the breakout session, unless there are questions. Let's see if there are some questions or.
Well, we're still assigning the rooms, so it might take a few minutes. So please feel free to ask your questions at this point.
Joel, this is John.
Yes.
I'm wondering, is it possible, I don't know if that can be changed, but instead of the 60-second warning, could it be like a 5-minute warning just also, or is that possible, or is that like a setting? And if that's a setting in Zoom, don't worry about it, but I'm just thinking 60 seconds, we might go into a panic.
The warning maximum could be 120 seconds, unfortunately.
Okay, we'll take it. We'll take 120.
Good job, John.
Okay. Great, and as we are waiting for you to be sent to the breakout session again, those of you who joined a little bit later, we would appreciate very much if you can fill the survey that was sent to you. That again is requested by the National Science Foundation when we organize workshop, but also provide us with great feedback on how to improve our future workshops, especially if they continue to be online for some time.
Joel, has the survey been sent already, or was it to be sent at the end of the session today?
I sent it earlier this morning.
Oh, okay. Excuse me.
Yes.
Pardon me.
Yeah.
I encourage you to ask questions now, that if you have not understood something regarding the breakout session.
Have the scribes been given the template slides?
Yes.
Yes, they have.
Okay.
We last night, if you are a moderator or a scribe, you should have received an email from us last night with the slides, the set of slides that will help you in your session. Again, it contains the objective, again, the slide with the objectives and what I just presented here, and a template for summarizing the key ideas at the end, and some slide in between for the scribe to take note directly in PowerPoint. Kurosh, can you give us an update?
Yes, I'm going to start the rooms and we'll just keep assigning people. So you might get thrown into your room and then more people will be added to that room as we go. So it might be, you might be a little late to your room by a few minutes, but we will continue doing this in the background. So with that, I'm going to open the rooms and we'll just continue filling people in. If you're stuck in the main room still, you haven't put in your primary room yet, just hang on for 1 or 2 minutes. And if you still don't go in, then we can continue talking, because I will be in the main room and you can let me know where to put you.
Joel, there is one question that just came up, maybe about the universal base frame, before Kurosh shifts us all out.
Sure, I do not see it here.
I think it's in the chat.
It just says, could you explain how the universal base frame works, from Maha?
I see, okay. So the universal base frame would be, a planar frame that is attached rigidly to the platen. And if you build, let's say, a building that has a width and a length larger than the shake table platen, it would rest on it. And ideally, this frame has to be such that you you would need to do a lot of analysis, I think, to make sure that when you, let's say, shake the building in 3 translation, including the vertical, that the boundary condition at the base are the same as if we had a rigid platen much larger, like in the ED fence. You cannot start to have, you know, the outriggers flexing and vibrating and creating some non-realistic boundary condition at the base. So it basically build something that would create the same effect as if you had a larger platen. Don't know if it answer your question.
He said thank you.
Great.
Okay, with that, I'm going to open up the rooms, send most of the people in the rooms, and if you're left behind, just wait a minute or let me know which room you'd like to go into and we'll assign you. Thank you. Okay, there's a few people left here. If you don't mind sending me a message so I can assign you in the proper rooms, please. Okay. I've assigned several. There's only 3 that have not been assigned currently, and I'm getting messages in the chat, so. Okay, so the breakout sessions will be closing in 2 minutes. We just gave the 2-minute warning, and everyone's going to join back in this main room. And we'll take a short little break and we'll continue.
Oh, it was so stressful, Kurosh, that 120-second warning. My group is sweating.
Yeah, we need one more hour, so we'll be back.
So what I can do,
can't go get a coffee.
Is since we have a break,
what I was
free to go back into
thinking
the
would be useful to keep the rooms open until it was time to start the next session, so that at least the moderator and scribe could finalize the slides.
Sure. I'm going to reopen the rooms, and whoever is going to be discussing the slides can go back into the rooms, and the rest of you guys can just take a break, enjoy coffee. I can make some announcements. But while everybody's here, let me make one announcement just to make sure everybody gets this. We sent out an email this morning, right early on at the start of the workshop. It's a survey that we're required to report the results to. So please take a few minutes before the end of the day and submit your feedback and help us out in organizing and arranging our future workshops. We'd greatly appreciate it. Every response you submit is anonymous, so just please be genuine. Feel free to speak your mind and let us know what you think we can do better or what we're doing well enough already, or whatever. Okay, I'm going to open up the room, so whoever needs to go and discuss can go ahead and discuss. And the
so how long is the break?
15 minutes.
Okay.
Yep. All righty. Another announcement I can take this opportunity to make is if you look at the agenda, you will see that we have some office hours scheduled, one-on-one sessions if you'd like. After the workshop, the workshop is supposed to end at around 12:45. You can go have a lunch and 12:45 Pacific time. Have a lunch, and starting at 2 o'clock, we will have Professor Tara Hutchinson and Professor Vandeninde available from 2 to 3 p.m. Pacific to discuss any of your questions or future proposals that you'd like help on. And at 3 o'clock, we have Professor Conte. Now, I'm not entirely sure if anybody plans on participating, but we are available to help and have one-on-one sessions with you all during those times. The links for the Zoom meetings for those office hours are available in the agenda file. So please take a look at that if you're interested. Also, another reminder, we're always available to answer any questions you may have. If you don't have any questions right now, please feel free to shoot us an email. We'll get back to you as soon as we possibly can. Right now, I'm going to go ahead and put my own email address in the chat box, so you can all have it on hand. And if you have any questions or concerns for the future, please, again, feel free to email us.
Kurosh, I like this, whatever the Zoom versions you have to have these breakout rooms and automatically go to the breakout Zoom and come back to the main room. This is a nice feature.
Yeah, thank you. This is my first time experiencing it, and I like it. I think it works pretty well. It was a little difficult to set it up initially, but I think once you set it up, it's pretty sweet.
That's pretty sweet, yeah.
Thanks for the feedback. I appreciate that. I'm glad that the experience was nice on the other side too.
So we are ready for the summary of the breakout sessions.
In about 1 minute, the rooms are closing in 60 seconds.
Oh, I see.
So
Okay.
if we can wait 1 more minute, that would be fantastic.
Sure. In the meantime, if any of you has some questions, please do not hesitate. So the goal again is to have short summary, 3 minutes per group, and so that we have plenty of time to discuss. Maybe we should reserve the question after all the summary. It's better, I think.
We just have one slide. So Joel, Kurosh, can you allow Sergio to share his screen, not mine? I had to completely reset my computer, so.
Yes, I will make sure.
That's basically working with bare bones right now.
Great, Jose. So you will be the first one, right?
Oh, I don't know.
Yeah, if you can.
Okay. Yeah, mine will. Yeah, I will do that.
Oh, the stress, Kurosh.
You guys did it to me again. I was like, we've got 30 seconds, paste it.
Good job, Kurosh.
So everybody is back from the sessions, Kurosh?
Who presents first? Joel?
We'll go in the order of the number of the session if possible. So 1 concrete, 2 steel building, 3 timber, wood frame, and so on.
Okay, I'm not first.
Unless one of you has to leave early and wants to present earlier, just let us know.
Will everybody be able to have audio? Because we were going to co-present ours. Is everybody on audio if they need to be?
Yes, everyone can unmute. Okay. Yeah, everything should be fine.
Thank you.
Yeah, same thing for when we will have the question. Everybody will be unmuted, so talk whenever you want. We try to avoid having people talking at the same time. So I think, Jose, you can start.
Okay, so if you Kurosh, if you do me a favor and enable Sergio to share his screen.
I think I'm sharing screen. Nobody sees it.
Oh, yeah, I see it. Right.
Okay, great.
Okay, so if you go to the slide, the summary slide, Sergio, please. Oh, let's first of all, let's go on show who participated in our session, and then we go to the summary. So we had 5 participants in our session. So we had Juan Sebastián Zambrano from Universidad de Cuenca in Ecuador, Professor Julio Ramirez from Purdue University, Maha Kenawi from University of Nevada at Reno. She's a postdoctoral fellow there. Anthony Trogovich, who is a former student here at UC San Diego and is a lead structural engineer, John A. Martin and Associates in the Bay Area, and Govardhan Bhatt of the National Institute of Technology at Raipur. So we had an excellent session with most participants giving input to their research needs. And following the recommendation, we look at 3 potential topics. One is into the shear strength of core walls in tall buildings. The second one on backstage diaphragms. And the third one on the use of high strength reinforcing steel as in lateral force resisting systems as longitudinal reinforcement. So if we go to the summary, thank you, Sergio. So in what happens, to give you a little bit of background information to you all, with the advent of tall buildings in the West Coast of United States, in particular Seattle, Bay Area, and Los Angeles, and even here in San Diego, we see that structural walls in the way of core walls or just isolated walls in these buildings are making use of high strength concrete, 10,000 PSI or so, and they're taking, to minimize the section, they're taking these walls to the maximum shear stresses that are allowed by the ACI code. Now, the provisions of the ACI code were not developed for these walls of this size. These were developed mainly for thin webs of I-beams or so. And we have been using those here to basically limit the amount of shear stresses these walls can take. Now, we don't have a lot of knowledge on if this is applicable or not. We have no knowledge if we have size effects, and we don't have sufficient computational models to look into this problem. So this basically offers a unique research possibility of using the shaking table as to basically do a capstone design project. And this is no different from the projects I work in the diaphragm seismic design methodology, and similar to what John and his collaborators are doing with the tall wood building project, where we do a series of tests, build up the computational models to a significant level of understanding, and then go and do a final capstone project. So since we're working here in these core walls in buildings with very large sizes, it's impossible to test these at full scale. But certainly in different universities, we could test a number of core walls with different geometries and so on as part of a collaborative effort, calibrate different tools of different detailing finite elements, and then come and do a capstone here. I think by talking to Julio Ramirez, Professor Ramirez, these large research programs can be, for example, taken from NSF or NIST or both, and using the science plans that are in NERI as collaborative programs. The second topic is on backstage diaphragms. And for those of you, it's a very specific name or so. So you have a tall building, let's say 20, 30, 50-story building anywhere on the West Coast. And then those buildings are not just a single tower. And in the lower floors, they spread out like a podium. And in many cases, they actually go on the ground 3, 4, 6, or 8 levels as well. So now when you have the inertia forces coming from the tower and into this podium, they disperse and they look to a lot of these inertia forces get into the retaining walls or to the walls that the architect has placed in this building. So this looks like a very elementary problem, but in practice, many structural engineers use black boxes, upper and lower bounds, but they don't even know if this is an upper or lower bound. So we know very little about this. It's again, these are extremely large size elements, and they lend themselves to do some scale testing on the base frame that Professor Conte mentioned, so we can expand out of the platen as a capstone project of several studies that will extensively use computational simulations. Again, following the framework and the mold of the Niels-Stolwood program, or the DSDM programs in which I worked in the second one, I think this could be a very successful venture as part of a collaborative effort. These are large programs, of course. The final one is topic 3, is that now the trend, ACI has enabled now to use high strength reinforcing steel, which is grade 80 and grade 100, and for particularly grade 180 for the lateral force resisting systems in core walls and structural walls in buildings. And the aim of this is basically to reduce that significant congestion we have in these walls. Sometimes it gets very, very congested in buildings in either Los Angeles, San Francisco, in the Bay Area, or in Seattle. So the idea is to use these higher strength reinforcing steel to reduce congestion. But the thing is that we don't know much about the dynamic behavior of this reinforcing steel. They come at higher strength but reduce ductility. So it will be great to again go from the bar in air testing to component testing and end up with a capstone project on the LH Post 6, where we are able to test at some kind of a scale buildings and compare or try to get some information about grade 100 reinforcing steel, sometimes even greater. I know Anthony Trogovich mentioned that in some cases they use grade 150, but no for longitudinal reinforcement. But there is a lot of interest in the community to implementing higher grade reinforcing steel. So those are the basic 3 topics that we discuss in our group. And I would like to pass it to our second subgroup that's looking to another topic.
Yes, thank you very much, Jose. So Jim Malley now will summarize for his group.
How do I share? Let's see. Let's see. Trying to figure out how to share my video. Oh, there it is. I'm sorry, I lost it there for a second. Let's go there. Okay, can you see it all right?
Yes.
Okay, great. So the steel building structures topic. I'm going to try and start my stopwatch and stop at 3 minutes. And so the next is the group. The participants, myself and Amanpreet Singh from UCSD, did a great job as our scribe. Hernan Castaneda, PhD student at UMass. Devin Huber from AISC, the director of research there. Jakob Valagura from KPFF in San Francisco, design engineer. Barb Simpson, assistant professor at Oregon State, and Paul Richards from Durfuse. And we also had a very good conversation. So we had 3 topics. The first are what I'm calling Bssc rocking systems. This came out of the Bssc research study that Bill Holmes talked about this morning, and it was the one primary steel topic in the document based on some work done by ATC 116. What we find is that many standard code type shorter buildings, brace frames especially, will actually rock rather than before they actually buckle braces or yield the BRBs, and if they're on spread footing foundations. So it would be helpful to know how those systems are actually going to behave, what the interaction would be with the rest of the building, etc. And then you could also design some intentionally rocking systems. There are other countries that have provisions for rocking designs that we could compare and contrast with our standard systems. We thought about doing fixed base test, and then a rocking base test, just allowing it to bounce on the table, and then potentially even using the soil box and getting soil structure interaction. So that was the first thought. The second is steel wood systems in combination. Thought maybe John Vanderlint in the group would be interested in this because it seems to be fairly popular to try and combine steel lateral systems with some of the CLT gravity systems, and a lot of the interactions with diaphragms and how those are all going to work would seemingly be a very interesting test to have done on the table. Really could incorporate some of the resilience concepts as well into that topic. And then our final one is a little more open. We didn't kind of get too detailed on this one, but the idea was to look at a main shock on a system, whether it be an older system, not a complying system, and also complying system, so we could have two prongs in the program, and then do some damage assessment after the first test to decide how you might want to repair it or not repair it. Maybe if you didn't think you needed to repair it, do an aftershock test to see what happened there, and then potentially repair it, and then maybe do the original shock to sort of kind of put the specimen through its paces. And really there's not very much information on kind of post-earthquake response to aftershocks, as well as repaired and then retesting. So that would be the third topic that we thought about. So with that, I think I'll turn it over to the next presentation.
Yes, thank you very much, Jim. Number 3 will be John Vanderlint on timber wood frame building structures.
All right, let me. Okay, hopefully you guys can see that. We're going to do a group presentation here, so we'll each hit one bullet. And so with that, we also want to just acknowledge our scribe, our participants. We were a smaller group, so it was myself, Larry, and Steve. And with that, let's see, I think we said, Larry, you'd be first, and then Steve, and then me.
Right. Yeah, thanks, John. I also just wanted to say it's a real honor for me to be able to participate in this workshop. And I always enjoy working with the researchers at UCSD. So our first idea for wood had to do with developing a research program to look at inexpensive response modification devices that may be dampers or base isolation, something that would serve to improve performance, reduce damage. And looking at that second bullet first, being able to utilize the vertical component, or look at the vertical component with the changes on the table might be very useful based on previous base isolation research and things. And then also we talked about simplifying the code provisions that exist right now that are kind of a barrier to implement this sort of response modification into light frame wood construction. So research is always good for moving things forward. So with that, I will hand it off to Steve.
Thanks, Larry. Thanks, John. And good morning or good afternoon to everybody who's here. The second bullet point was really derived from another research opportunity that Bill Holmes mentioned this morning. And that was as part of the ATC 116 project that we were involved in. We've taken a really hard look at short period structures and what affects their collapse resistance and the performance. And for light frame wood, it was very apparent that one of the key performance indicators is just really brute strength of the structure, kind of a ratio of peak capacity to building weight. And so more research needs to be done there to try and develop some, I think, simplified provisions for wood buildings that can take kind of a larger holistic look at their entire performance to come up with better performing structures that really don't have to cost much more than they do now, and to get those building code provisions developed that would support that. And with that, I'll turn it over to John.
All right, thanks, Steve. And Jim, I'll just add, we did actually have some discussion on the wood-steel combination, kind of right up that alley. So I think we all love the topic. We don't have it down here, but I'm glad you did. So functional recovery of wood buildings. I think this is, obviously this is a huge topic with the ongoing work with NIST and others, but and I think there's a lot of NSF projects that are focusing on this. And so it's really finding that balance between the structural and non-structural components and how those can, in a way, people focus and they look at a single component or a couple of components, but how do you get them all working in concert is kind of the thought process here. And then, really, and this is maybe more overarching, it's really that motivation for actually doing it. But that's, how do you determine what the building performance should be to achieve certain goals or objectives at the community level? So it's really almost like in a sense, it's a de-aggregation, except that we can't do it that way. So we'll do it forward and we'll just iterate. And so I think that's in a way critical. And then we, just for opportunities, I'll just close by saying that, as Steve kind of indicated, we thought we'll just add one bullet here, but really most of the collaboration comes from the development of commodity and proprietary products of both. And these all require industry and academic collaboration throughout. So we see industry as being a key participant in all these project teams that are related to wood. And with that, that is our summary. So let me stop sharing and pass to group 4.
Thank you very much, John. Group 4, Georgios Tsampras on seismic retrofitting of building structures.
Yep. Let's see. Okay, can you see my screen?
Yep.
Perfect. Okay, so our group consisted of Leo Panian from Tipping Structural Engineers, myself, Professor Benson Singh from UC San Diego, Alex Lee from Southern California Edison, Bill Horstman from Pacific Gas Electric Company, San Francisco, Sina Yusefiano Dam from University at Buffalo, I'm sorry, Sina, Ahmad Ali, and Kushai Akuli, Saif Hussein, Professor Guido Kamata, and Lee Shun from UC San Diego, who took also the notes, so thank you, Lynn. So our team worked on the seismic retrofit schemes. And the first topic that we focused was the retrofit of mid-rise welded steel moment resisting frame structures. Well, the issue identified there was that we have the weak story mechanism And more specifically, the weak story mechanism drives the demand to column splices that have a potential fracture issue of the partial penetration weld. Also, the shear connections the gravity beams faced are problematic because of this weak story mechanism, and we may lose our capacity to carry the gravity load. So we identified that there is a need to basically use this opportunity to utilize the shake table in order to assess the dynamic effects in these steel moment resistant frames, and basically try to evaluate retrofit schemes that may utilize different configurations of seismic response modification devices, such as backline strain braces, to control the distribution of the load throughout these vulnerable frames. The second topic was related to the out-of-plane behavior of unreinforced masonry structures. Now, it is, I guess, from a research perspective, it is a great opportunity to utilize the multi-directional ground motion capability that we will have with the LH Post 6 in order to combine this lateral ground motion with the vertical ground motions in order to evaluate the seismic capacity of the unreinforced masonry, specifically the effect to the out-of-plane behavior. We discussed about the need to better understand retrofit schemes that utilize FRP in order to provide this additional out-of-plane strength. And also we touched upon to the importance of understanding the effect of infill walls in the global response of building structures. And this is mainly because of the non-ductile response, and how can we address that? What is the detailing that we need to use in order to make sure that we don't have negative effects of these infill walls? The last topic was related to the seismic gap between buildings that have different dynamic characteristics. So sometimes there is an issue with one owner basically has few buildings that are adjacent, but they have different dynamic characteristics, and there are limitations in the seismic gap. Instead of trying to increase the seismic gap, which is impossible, you can tie the buildings together using seismic response modification devices in order to control the forces that are flowing from one system to the other. So one idea was that we could utilize the modular frames that we discussed in order to create, let's say, two buildings with different dynamic characteristics, couple them together in order to see the effect on the dynamic response of these modular frames, but also assess the effect on the non-structural components that may span between these two buildings. And again, this comes back to the idea of utilizing something that the shake table can provide and have repetitive types of tests. Yeah, that's it.
Thank you very much, Georgios. And now session number 5, Anthony Sanchez on bridge structures.
Okay. Can you hear me?
Yep.
All right, good. Let me pull up our PowerPoint. Okay, good. All right, can you see that?
Yep.
All right, good. All right, so our participants were myself, Anthony Sanchez, Jianyu Cheng, who's a PhD student at UC San Diego, Charlie Sikorsky, who's retired from Caltrans. He used to be the research, one of the research managers working with UC San Diego on research topics. Now he's with ITS at UC Berkeley. And Petros Sideris, assistant professor at Texas A&M, who has been doing research on low damage bridge systems. So our three topics are damage resistant bridge systems, foundation rocking, and different topics related to durability. So topic one, damage resistant design. We were taking this to mean unbonded post-tensioning in columns to reduce damage in plastic hinges and self-center the bridge after an earthquake, and also sliding and rocking joints. And this research has been done. Some research has been done already at UC San Diego, UNR, Texas A&M, University of Washington, and Buffalo. So there's been tests, but there's no clear path on how to implement this into practice. Charlie pointed out that it would be difficult to convince Caltrans and the other DOTs that it could be beneficial, and the benefit has not been quantified yet. It's difficult to do field demonstration projects. If you did a demonstration project, you'd have to wait, it could be decades for an earthquake to happen to test it. So we do need full scale or large scale testing, but this funding may be difficult to obtain. It tends to be pretty expensive, maybe $1 million to $2 million per test. Also, the DOTs and the state bridge engineers are comfortable with the current design methods. They work well. They've been tested. They're in the codes. They've been proof tested during earthquakes, so everyone's comfortable with the current seismic design criteria and the ductility methods. So we think it'll take time to convince the DOTs that we should start doing this testing. I think if we quantified how much money can be saved, that seems like that would be a relatively inexpensive desktop study to show, based on past earthquakes, what the level of damage was to bridges, and if some of these bridges had these damage-resistant systems in place, how much money could we have saved in current dollars, and then also quantify other impacts, such as reduced impacts to traffic. For example, if a bridge does not collapse but needs to be torn down and replaced, that's going to have a big impact to traffic. So what is that in terms of impact to the economy? There should be a way to quantify that as well. So I think if we can show the benefits through maybe a low-cost study, rather than doing the trying to do the shake table testing right away, that could lead to more funding for the shake table tests. All right, so that's topic number one. Topic number two is foundation rocking. So this is where either you have a spread footing that is allowed to uplift and rock, or if you need a pile footing, like we have shown here schematically, you build the pile footing that you need, but then you put a reduced size spread footing on top, and that spread footing now can rock on top of the pile cap. So the idea here is that this rocking would occur before the plastic hinge forms. So you can reduce damage to the columns. You would never get a plastic hinge. The system would stay elastic, and the energy is dissipated, and the displacement capacity comes from rocking of the foundation. So this seems like a great approach if if this can be implemented, it seems like it's a low cost. It could actually reduce the cost. For example, if you have a good design methodology to allow spread footings to rock, you can make these spread footings smaller than you otherwise would if you don't allow uplift. So you can reduce the initial capital costs for new bridges, and then also reduce damage and future costs of replacing damaged bridges. So it seems like it's a win-win there. The problem is the current mindset of the industry is to avoid foundation rocking. A lot of the bridge engineers are used to not allowing uplift in footings. They want to make the footings bigger, to put tie downs, kind of a brute force approach to resisting the seismic loads, but it's actually, I believe, going in the wrong direction. We want our bridges to be more flexible, not more stiff. So we need to change that mindset in the industry. And I think we need the research to back it up to show that it is a reliable mechanism for dissipating seismic forces, and that it's ways to assess the stability so that we can be certain that the system is going to be stable, and then come up with some easy to implement design methodologies. So I think there's a big opportunity to do some research there to show how we would design these rocking systems. And then also a big topic of the bridge industry right now is accelerated bridge construction. So it seems like this would be very well suited to ABC, where you have these precast components. And if you can just take a precast footing and set it down on top of a pile cap without any monolithic connection, that's ideal. So I think we can work with, maybe there's funding available for accelerated bridge construction that we can combine to show these rocking systems. All right, so that was topic number 2. And then topic number 3 had to do with different ways to increase durability in bridges. Some of these may have applications for the high performance outdoor shake table. Some may not have applications. For example, ultra high performance concrete for bridge decks. So the DOTs are spending a lot of money now rehabbing and replacing bridge decks. They get the most wear of any part of the bridge. That's where the live loads are hitting the deck. They're getting impacts, and they get beat up over the years. So if we can come up with more durable bridge decks, that could save a lot of money, reduce maintenance costs. We were talking about doing long-term degradation testings could be for the rocking foundations or for the damage resistant systems. So where we would test them, build them, test them initially, and then just let them sit and potentially do some aging, some accelerated aging, whether we're spraying them with salt water or putting some kind of live load on them to see how they degrade, and then testing them later. So that would give us a more realistic way to test these bridges in service, right? Because if we build one of these bridge systems, the earthquake's not going to happen immediately. It may happen in 20 years or 50 or 70 years. So we'd like to know that these systems are durable, and that see what they respond like, how they can withstand earthquakes once they've deteriorated or been in service for a long time. And then we're talking about doing live load testing on the shake table. So I know all the discussions have been about doing seismic testing, but maybe there's a way to use the outdoor shake table to simulate live loading and to simulate many cycles of live loading. That could be good for testing the durability of bridge decks, or also testing fatigue in steel members. So that was our topic number 3. There's a picture of the a deck that I showed yesterday. It's a bridge in Stockton that Caltrans is spending millions of dollars fixing this deck every few years. And then potential funding sources. We all decided that NSF is not a good source of funding when it comes to bridges. They defer to FHWA for bridges. So you have FHWA, and then you also have all the state DOTs, especially the ones in seismic regions. So of course, Caltrans, WashDOT, also Alaska DOT, Oregon DOT, Hawaii DOT, and also Idaho and Utah. So there's our summary of the 3 topics.
Thank you very much, Tony.
All right, you're welcome.
And now let's go to Amarnath Kasalanati on earthquake protective systems.
Thank you, Joel. As soon as Sanchez releases, okay, I will share the screen. And, good morning, everyone. It's still morning. Can you see my screen all right, John?
Yes, yes.
Okay, great. Thank you for the opportunity to be in this session. And we had a very good group. We had good representation from academia, manufacturer, a practitioner, and also many people who have used protective systems internationally were there. That is just captured in 8 people you see here. I want to thank Claudio Sepulveda for being the scribe and taking excellent notes. Like all other groups, we were very excited about the large size of the table, as well as the opportunity to apply multi-directional excitation. That is the same for all researchers, but specifically for isolation and energy dissipation fields, as well as rocking columns and such. The ability of this table to reproduce the motion in low frequency or long period content, that is of great importance. Some of the smaller tables cannot do that, so we cannot push the isolated structures quite as much as what they see in the field. So this table provides that opportunity. And also we are excited about the rotational motion and what it means. Of the different things we discussed, we identified 3 topics, and one is the ultimate behavior of devices as well as structures with the protective devices. And Professor Mosqueda contributed to this, and basically as the design level motions, that behavior is well understood. But what happens at MCE and with the superstructure yielding, how do these devices interact? And again, this facility with its size and performance capabilities will provide opportunities to test bearings to limits and study what happens to the overall structure and design. The second one is about improving code equations. When you have systems with intersecting lateral systems, you use 100 plus 30% type of equations, which may be unconservative, but 100 plus 100 would be too conservative. So what is the right combination? Those kind of things. Here, it can be combined with what was discussed by the previous breakout groups. Doesn't have to be an isolated or damped, but you can have the damped ones or isolated ones later. For example, in the code, very often you use a combination of hysteretic damping in the superstructure combined with the supplemental damping in the devices. But large structures have not been pushed to the yielding and limits to validate some of those equations. Again, this LH-POS6 will provide opportunities to do that. And then the third one we discussed is the vertical motion and its impact on response. Many of you know of the testing done at eDefense led by Professor Kerry Ryan. It answered many questions, but it also raised several questions about the vertical motion and performance of non-structural components. And it is one data point. There are several papers, but we can add more data by replicating some of those on LH-POS6 and understanding the vertical motions and its impact. So those are broadly what we discussed, condensed into 3 topics. As for the funding sources, the usual suspects are there, NHS, FEMA, and so on, but California resiliency is talked about a bit. Perhaps we are not taking advantage of it as much as we could, or we should be more involved. That is one that is identified. Again, another usual suspect is any high-tech company that have a lot of data centers, talking to them about isolating, damping their structures. But more importantly, a representative from Taylor Devices was in the discussion and has kindly offered to provide dampers. Again, depending on a lot of things working out, size and type of experiments, but that was one thing. And also reaching isolation system manufacturers. The previous large-scale tests, they were very large combined efforts with manufacturers contributing. They will play a key role in making some of these tests happen. Electrical systems could benefit from this research, so that is another source we identified. And then taking advantage of that test bed that Joel mentioned yesterday about reconfigurable, perhaps go to yield and replace some things, and how do we take advantage of that? So that's another one. Basically, the concluding thought is, the SRMD test machine in San Diego that's been in use for about 20 years. Its work, it had made from research into practice and into code with lambda factors or bounded design and so on for isolation and damping. The hope of this group is LH-POS6 will do the same for system level performance of structures using protective devices. And again, I thank all the participants in this group. Joel, back to you.
Thank you very much, Amarnath. And now let's go to number 7 with Jorge Meneses on geostructures.
Okay. I'm going to select, I'm going to share my screen. All right. So this is a breakout session on geohazards. My name is Jorge Meneses, and I serve as the moderator. Maitreya Kurumbati from UCSD serve as the scribe. This is the list of the participants. Myself, Maitreya the scribe, Bill Black with Mead and Hunt, Ramin Motamed with the University of Nevada, Reno, Teresa Richards, UCSD, and Zia Safir Kleinfelder. Initially, what we did is we did a kind of brainstorm just to identify some potential research areas or topics. So first of all, I would like to emphasize that in the field of geotechnical earthquake engineering is very, very important large-scale testing. In the past, traditionally, has been in the within physical modeling, small-scale testing has been performed. 1G small scale testing, and also centrifuge testing. However, there are some, of course, advantages, but also there are some disadvantages doing this small scale testing. We can capture important information doing this type of testing, but also at the same time, when we perform large-scale testing, as we can do here using the LH Post-6 facilities, is that we can have a better picture of the issue that we want to identify. We are going to discuss something about this later when we identify some issues, but I think that this is the very important thing, at least in geotechnical earthquake engineering, the large-scale testing component. Possible research areas study the behavior of piles, foundations in general, pipes in saturated sand under earthquake forces, behavior of shallow foundations in liquefiable soils. Large-scale testing can complement existing available centrifuge testing in this area. Performance design of retaining structures. Yesterday, Cici Nicolau did a very, very important presentation about this topic. And I think this is something that has to be pursued because there are still many things that we need to investigate and evaluate for appropriate characterization of the distribution of the seismic lateral earth forces on retaining structures. Also, another topic that we discussed is input motions, how the input motions are used using this facility, the importance, for example, of near source versus a far source, the importance of short duration versus long duration, subduction versus shallow crustal, etc. Fault rupture, of course, is something very important that Craig described yesterday. And also another topic is, for example, things like interaction of concrete dams with reservoir water. Each one has a different frequency of vibration, and this interaction could be something interesting also to evaluate. So we selected 3 topics based on this discussion. Number 1 is, in general, behavior of foundations, shallow and deep, pipes in saturated sand under earthquake forces. Basically, we're interested when, for example, during the shaking, during the ground motion, soil liquefies, right? We are interested in effects of liquefaction and the induced lateral spread on foundations and also pipes. If we are talking about this type of elements, of course, we are talking basically about, for example, port facilities, harbor facilities, and also we are concerned that in the future, probably in the next 50 years, we have to address, and we have to address from now, experimentally also, the effects of climate change. Like, for example, the sea level rise will contribute to the increase of coastal areas subjected to liquefaction and lateral spread. And this effect has been needs to be studied using this large scale testing. So this is something that this facility will contribute a lot evaluating these effects. Another thing that was discussed yesterday, presented by Cici, and we would like to see this pursued, is a study evaluation of performance and design of retaining structure. In the field, in the literature, we see there will be some information about small scale testing, physical testing, centrifuge testing, but there is not much information about retaining structures. So this is something that we believe will contribute a lot more to understand better the behavior of these structures, depending upon the type of the backfill, depending upon the type of the wall, restrained versus unrestrained. All these variables need to be investigated. And we believe that there is not enough experimental studies. And we think that large scale will complement current studies using the centrifuge. This is something that is needed urgent, especially in the practice. Another topic is about input motions. So especially, when we are dealing with non-linear time history analysis of structures and their performance-based design. Is needed to develop time histories. There is still some many aspects to cover. It's not only from the point of view of engineering seismologies, the study of the ground motion herself, but also at the same time it's important to see how certain characteristics of ground motions affect the response of structures, affect the response of the models that are tested under this facility. So what are the criteria to use input motions, how they are developed, how they are selected? Are they considering near source effects? For example, in near source effect, there are certain characteristics. For example, the poles, how the poles will affect the presence or not of these poles will affect the response of a model sitting on these facilities. So this is something that I think needs more discussion and also needs to be investigated, how this aspect of testing is addressed depending upon, of course, the testing that is being done. So also we discussed some potential funding sources, of course, NSF, Caltrans, PIRT, Department of Neighboring States. There are some that are willing to support this type of studies, testing, probably industry partnership with LADWP or some energy companies. Ports, we believe that could be very interested also in this topic, especially with the sea level rise. Port of LA, Port of Long Beach, California Earthquake Authority, probably other federal level agencies such as the NRC, the Department of Energy. I think this is basically the summary of the three topics that we are somehow that we discuss and we are suggesting for future for consideration under Geostructures. Thank you, Joel.
Thank you very much, Jorge. And the next one, number 8, Lifeline Utilities by Craig Davis and Elide Pantoli. I don't know who will present. I think Craig, yes.
Yes, I will present. Can you see my screen?
Yes.
Okay. Yeah, so the breakout topic is lifelines. I am the moderator, and Ilde Pantolini, Pantoli, sorry, I mispronounced that, from UC San Diego. We could skip these slides that was there from the description. Our participants were, excuse me for not necessarily getting all your names correctly, but Boris Jeremic from UC Davis, Ming Wang from UC San Diego, Soji Wu from EMD International, Christian Fausto, a master's student and works for Southern California Edison, Sissy Nicolau from WSP, Gloria Ferroni from UCSD. Some of these had to come and go at different times during the session, and we had, I think, a good mix of discussion between research and industry. I want to give a quick background slide on the focus of what we're going to present as our topics. So we had targets based on topics that we proposed are based on unique capabilities of the LA Coast 6 that it provides. I don't think that's a well-written statement that I made, but I hope you get the understanding. And to improve the existing design philosophies, for example, recovery-based design rather than damage-resistant design. We're talking about systems here for Lifeline and the ability to provide service, that type of a concept that requires much more in-depth discussion and research on its own. And I'm going to present some high-level topics that we concluded on, which may be different than earlier discussions. You know, we're not talking about high-strength rebar. We're talking about systems. So the ideas of these details that you've heard in many of the earlier presentations need to still be fleshed out as each project goes forward. So these high-level topics really could be long-term programs in them into themselves. And each testing scheme requires more detailed descriptions on the materials, structural and geotechnical issues, and so on, targeting specific types of knowledge to be gained by the different tests. So we're going to actually present 4 topics in 2 slides. So I think my 3 minutes start now. The topic 1 is systems testing of lifelines. So this was summarized in my presentation yesterday. So we're going to investigate the interaction, the interconnection of components within stations. For example, electric power substations are commonly used, but there's treatment systems, treatment plants, and water and wastewater. There's the refineries and many other types of components related to all these different lifeline systems that we're talking about. So it's a general topic. We're trying to give a vision of what it is. They all interconnect, right? So this big table gives us an opportunity to either do full-scale or potentially scaled models of all these different components and how they interconnect. And instead of looking at each one separately, you know, they interact. So we're able to look at that. And then from that, we can start looking deeper into the fragilities of each of these components and the different types of designs that you might have. Just for each of these components, there's many ways of designing them, right? So you take ATC 58, I think that's the right number, on fragilities of buildings. And they began to focus on different types of structural types, different structural types. And so you can think about that for transformers. There's different types of transformers and the bushing, and then how they're connecting to other types of structures. There's different ways of running the lines. There's different types of these alternate structures and how they all interact. And then there's layouts within these facilities, right? So you have a wide, you actually have an infinite number of possibilities, but you could actually start narrowing these down to very common types of layouts and very common types of materials and designs within each of these components and how they all interact. So then topic 2, tall structures with 6 degrees of freedom being tested. So lifelines have many unique tall structures. Some examples are the wind turbines, outlet towers, smokestacks. The list goes on and on and on. So think of these tall structures. Now, small rotations at the base make a big difference. We saw that in a presentation yesterday. I forgot exactly who it was, but I think they referenced one of my PhD advisors, Professor Kukunik from USC, in one of his research studies showing how that makes a difference. So not only that, but the multi-directional shaking makes a big difference. I made reference to recording in the LA 80-foot high or 100-foot high, I think it was LA Reservoir Outlet Tower, that swung, I think, 10 times, and 1G recorded in both directions. So that means it's swinging in a circle, right? That's a very big difference in stresses in the members than when you're shaking it 2D. So you might think about going back, first and foremost, to this wind turbine, testing that same wind turbine again with these multiple degrees of freedom to start to begin to understand how these multiple degrees of freedom actually do make a difference. Start documenting that, and then create a program where you're systematically testing these different outlet towers with different materials and retrofit schemes and so on. Topic 3 is long linear above ground structures. Yesterday I gave a presentation on pipelines, but there's also transmission cables, and when they're shaking them in different, they swing and they can hit each other and create faults. And so there's all kinds of different long linear types of structures. Here we're talking about above ground. I get to below ground in the next one. So we need to investigate the differential behavior of the foundations from wave propagation and different soil conditions at each site, and how the supporting affect the supported components behave, the wires, the pipelines, the concrete slabs, and so on, with out-of-phase motions between these different supports. And from this, and actually it applies to some of the earlier parts, I think topic 1, we should think about extending the size of the table. So we're not necessarily talking about large or massive structures, but maybe we could use the capacity of the table to allow for cantilevering out to test more in this area for topic 1, right? When we're looking at systems and for the lengths of these long linear structures. So we challenge people, researchers, to think about that. And then topic 4 is below ground structures or underground structures. There's many unique and complicated structures, box type structures and pipe type structures, or cable type. I talked about it as a type. And so I referred to presentations yesterday, but I itemized some topics here. For sake of time, I talked about these in my presentation yesterday, so there's more detail in there. But these are the 4 types of structures, or 4 types of programs, actually, that we recommend this to be taken on. So, Joel, these could be very long, decades-long programs that get integrated into the testing. Potential funding sources would be maybe combined NIST, NSF, and industry. The industry may provide less funding, but more value in kind resources, material, engineering, and input from a practical industry perspective. Then there's other federal agencies, EPA, DOE, and so on. So think about, communications. They have many different types of federal agencies governing them, and state agencies. So these are types of things that could be addressed for funding. And I'm going to leave it there for the next.
Yep. Thank you very much, Craig. Thank you very much.
Oh, sure.
Number 9, Professor Tara Hutchinson, talk about non-structural components and systems.
Okay, great. Just get the screen shared. Can you see the slides okay?
Yes.
Okay, thank you. Myself and Michael Morano, one of our PhD students, helped moderate and scribe this session. We had a very good discussion. Here are our participants. Robert Belvin from Construction Specialties, coming with an interesting angle of the architectural perspective. Nate Deibler from VMC Group, doing a lot of work on testing and certification of NCSs. Scott Harvey as an academic researcher, looking at equipment isolation and seismic protection, amongst other things. Hossein Mustafai from FM Global, they're doing a lot of work on earthquake losses and risk, brings a very unique perspective to the issue of the overarching issue of NCSs. And Derek Watkins, one of our former PhD students, has a rich career in looking at issues of qualification of equipment, piping, bracing, and the like. So we had 7 of us in this discussion. We discussed 6 topics, and in the interest of time, we were requested, of course, to bubble up the top 3. And the way we organized these was, what the general topic was, what some of the issues we each could bring to the table relative to that topic, what some possible solutions might be with LH Post 6 to addressing and contributing to advancing this topic, and there's definitely some impediments. In the interest of time, I'll just point out the topic and then offer up what our thoughts were on what the possible solutions were with the exciting advancements of LH Post 6. So the first topic was seismic force estimates for NCSs. In a global sense, our consensus was the general expression of Bssc just doesn't work well across the board. Perhaps it works for some, not for others, and there's a variety of issues I think one could bring to bear to recognize that. However, with LH Post and possibly the use of a universal base frame, for example, or the modular test building, that could facilitate experiments to study the Bssc distribution. That was one option. Another option might be, and of course there could be a long laundry list of structural configurations to study this issue, but fixing connections to the reaction mass and moving with moving and or flexible connections to LH Post or the universal base frame, that could also provide an opportunity to report seismic forces for semi-flexible connections. The second topic, I'm not sure that if there's an impediment in your screen for the top of the slide, sorry about that. Second topic was interactions between NCSs and interactions between the NCSs and the primary structure. So they're separate topics, but similar problematic and uncertain response issues that come to bear. We know that they're not always isolated components. We ask the question, are they synergistic or are they counterproductive? I think Professor Scott Harvey had some really interesting points there. Could they be aggravated? And if not, could we utilize flexible connections? And if so, could we utilize flexible connections? So some possible solutions to study with LH post 6. One, I think, healthy discussion was the idea of performing hybrid testing with the shake table, with the newly configured shake table, newly upgraded table. The computer model in that case would be the building. That would allow the researcher to easily modify the computer model to account for different buildings and configurations, whereas the NCS as a specimen would be the physical payload. And that would allow multiple, in fact, NCSs to be mounted and assembled and or arrayed onto LH post 6. The other natural thing, and I think the modular test bed has been sort of strategically designed to help out with collecting information in this regard, was to strategically lay out a program in a systematic fashion and use that 3-story building to deliver those interactions. The third topic was the responsive contents. The data that's out there has largely been limited to residential contents, shelving, really small contents. And Hossein really brought this up as an impediment in their work from the insurer's point of view. The reality is the data is lacking for large warehouse type of contents, especially those that are mounted, they're elevated. Pharmaceutical, mechanical equipment, manufacturing storage facilities, wine storage facilities were some of the ones brought up. The limitation there is that damage vulnerability functions are really not well developed because the experimental data as a basis to understand the damage is lacking. So possible solutions with LH posts, a natural opportunity to test at full-scale storage racks under multiple degrees of freedom input excitation. And then the parallel to that, or the follow-on, might be to investigate protective systems that could be utilized in this scenario to protect these large and heavy contents, often mounted on either single point or multiple point storage racks. So I tried to give us a little time back. Hope that was useful. I want to thank the colleagues who joined that session.
Thank you very much, Tara. And the last one, seismic qualification of equipment, Derek Watkins.
Hello. Let me share my screen.
Derek was multitasking, by the way.
Yeah.
We claimed him in our session.
Moderated one session, finished early, and I jumped into the other one. All right, so our topic was seismic certification of equipment. The participants are listed here. We had a small group, but a nice diversity from university to test lab to utilities to people who do seismic certification as consultants. Our priority research needs, topic 1 is commercial testing needs. We believe because the size and payload capacity of the LH post that a significant amount of commercial testing could be done there, potentially up to 2-3 months a year of testing for very large equipment that's currently being tested either at Berkeley or at the Army Corps of Engineers lab. To do that, the lab will need to have the certain accreditations and quality assurance status that it needs. It may already have some, may need to expand it. And then topic 3 was research needs. I guess on the industry commercial testing side, there's a variety of test standards that the lab would have to be certified to: IEEE 693, 344, and AC 156. We would need to know for different payloads, especially heavy equipment, what the spectral capabilities of the table are on the low frequency end and on the high frequency end. Some equipment, the standard for AC-156 is to test up to 3.2 Gs, 5% damped spectral acceleration. But for specific projects in 693 and nuclear, it could be higher, as much as 5 or 6 Gs, and then some narrow banded frequencies even up to 10, 12 Gs. The equipment, heavy equipment, is not going to be a problem for the table since it's designed to take so much payload. The most important thing would be that cost and schedule at this lab are similar to or competitive with other commercial labs that can test heavy equipment. The table would have to be outfitted with a sort of special platen on top of the platen that's sacrificial that you could bolt and weld to. And then instrumentation requirements. Some tests require actual direct displacement measurement at the top of the equipment, and then load and strain in the anchorage of the equipment. The accreditation that you would need on the commercial side is IAS accreditation or ISO 17025, which I believe the lab already has. Just needs to list AC-156 and IEEE 693 on the certificate. And then if the lab is interested in doing nuclear testing, it would have to be a NQA1 ASME quality assurance program. So I think that's a majority of what I can see the table being used for, and funding for that is by the individual manufacturers who are looking to achieve a seismic certification. On the research side, we think that because of the size of the platen and the payload capacity, there's some heavy transformers that have bushing failures in substation equipment that could be investigated on the table. And then another thing for substation components, as well as other interconnected components, is this need to put maybe 2 or 3 pieces of equipment on the table interconnected, especially substation equipment, and see how the interconnection causing load back into the equipment works. And then we don't know the current status of suspended ceiling testing, but if the table had a wall-mounted frame as well as like a elevated ceiling-mounted test frame, then you could do suspended ceiling testing. So that was it.
Great, thank you very much, Eric. So obviously you had a very fruitful discussion in the sessions, it appears, from this high concentration of great ideas that we just heard of. So it's excellent input for us. Now, in terms of time, we are close to the end. So maybe what I suggest is we take a few big questions that some of you may have. I mean, one that I would like to ask and hear your comments about is, you've seen the test on the facility here. They are very expensive, very large scale. And you also saw from some presentation and some from blind studies that were taken in the past, the modeling uncertainty in, related to the current prediction in our field are very large, if not huge. And do you have any suggestion on mechanism to get more mileage out of this very expensive test, to connect the researchers who focus, on numerical simulation, modeling, prediction, and so that we can maybe tackle this problem of modeling uncertainty and try to manage it and reduce it? That's one question that I would have, but please, if you have other questions, let's have some discussion.
Joel, this is John. I have a comment / question, but I know NSF originally, when NEES was going, of course, we all remember they had the Grand Challenge projects, which enabled people to have significant budget to be able to run fairly large tests, and then that went away essentially, and it became these collaborative projects where everybody's getting maybe a few $100,000, but it has to be pulled together. And I know a lot of people have argued, unsuccessfully, or suggested, I guess maybe not argued, but suggested to NSF that this was a good mechanism and things. And so one thought for getting the most mileage out of these, I wonder if there's a way, much like DOTs do these pool funded studies, and they pool their funds together. And I wonder if there's a mechanism to do something like that, because it happens, it does happen informally, but then I think there's the issues of who's running it, who's getting credit for things. And so I think if there was, it might be something like there could be a workshop on how to pull fund these big projects, where everybody, where the IP is worked out, things like that. But anyway, just to throw that out there, because I think the Grand Challenge projects, I think they served a great purpose. I'd love to see them come back, but I don't work for NSF, so.
Yeah, sure. I think the key here is the funding available to those who would focus part of their time and research on correlating, and not just have all the money, to do the experiment and build the specimen. Yeah.
Yeah, and maybe the last comment I'll make related to that is if there's a way to to move the structure off the table and then back on, for reuse, so it can be repaired maybe out in the field for a longer period of time. That would be huge, because getting $100,000 to repair a building is not hard if it becomes your specimen, but getting $2 million to build one is. So.
Yeah, thank you, John, for your comment. Any other question related to what we just heard, or to the workshop overall? No, maybe I have another question for, if Anthony is still here, Tony Sanchez. You recommended low cost study for damage resistant design. Maybe can you elaborate a little more? You mean numerical simulation studies first, or?
No, I was talking about an economic study to figure out what the extent of the damage was during recent earthquakes, and then to quantify how much we can save if we went to this damage resistant systems rather than the ductility based systems we're using now.
Okay.
That'd be in terms of replacement costs, damage repair, plus impacts to traffic. That has, you can put a dollar amount on the impacts to traffic as well.
Yeah, thank you for clarifying.
You're welcome.
Any comments related to this topic of a large universal base frame, so that we can expand the footprint of the specimen that we want to test? Some of them mentioned that in their summary briefly, but anybody wants to add some comments about that, the need for that, or what we should consider in thinking about that?
This is Derek. I would just say, from the equipment testing side, the 40-foot by 25-foot footprint is probably pretty good for most of the equipment we'd be testing. So the size is good, but we would need that kind of platen above the platen that you could bolt to or weld to. So a universal frame on top for testing equipment would be really nice.
Mm-hmm. Thank you, Derek. No more comments, so I think everybody is ready to go to lunch. It's very understandable. So let me take a few minutes here to, on behalf of the NERI and UCSD team, I would like to thank all of you, starting with the speakers and the excellent presentation, the attendees, and for giving us your input and your ideas that we just heard of, and the moderators and the scribes who help in the sessions. Thank you very much. We also would like to ask you to please feel free to contact us at any time, those of you who will be preparing proposals. So if you want us, for example, to give you our feedback on feasibility of test or specimens, feedback on proposed test procedure in your proposal. And we wish you the very best for your research proposal, because if you win, we also win. Be excited to work with you on your ideas. And then also ask you, please do not forget again to fill the survey for this workshop. Will be very useful for us and important for NSF. And also remember, this afternoon we also have 2 hours, I think 2 to 3 and 3 to 4, where we have what we call office hours, advising on some of your future proposal or projects that you would like to maybe discuss with us already. And also we would like to ask all of you who presented a summary, if you can share your slide with us, it would be great. And I think that's my list. Kurosh, do you have maybe anything else that I may have forgotten?
Oh, thank you very much. No, about the sharing of the slides, please, if you can, email them to me. I will put my email in the chat once again. And thank you again for attending and participating in our workshop. Maybe
last thing, I would like to give a virtual round of applause to Kurosh for his incredible help in organizing this workshop and all its logistics. Thank you very much, Kurosh.
Thank you. It's my pleasure.
That's it. So we adjourn the workshop, and thank you all, and have a great afternoon, and hope to see you soon in the future in person, hopefully next time.